On Monday, I tried to show you a lot of examples of Q-polynomial association schemes or cometric association schemes that aren't P-polynomial. They're imprimitive in almost all cases. On Tuesday, I mentioned that people have constructed primitive ones, and we talked about basic theory of distance regular graphs and how behind the basic theory of cometric association schemes is. And then on Wednesday, we started building some of those basic tools. And we talked about the Suzuki theorems, and I thought that I would run out of time, so I didn't prepare complete proofs of the Suzuki theorems, but I proved a theorem yesterday that very quickly leads to the Suzuki theorems. But two of the tools that I used, Dickie's lemma from his thesis, and this thing I called the boxed-in lemma, I didn't give proofs of because the best way I know how to prove them uses these tools called scaffolds. So I first learned about these things. I was on sabbatical at Waterloo, and I was reading these papers of Suzuki in 1999, and I sort of reverse engineered the tensors that Suzuki was using. But Suzuki wrote that he learned this technique from Dickie, from Dickie's thesis. Dickie learned the technique from Paul Terwilliger, and you can see this, you'll see tomorrow that a lot of these ideas are already in Terwilliger's paper in 1989. Terwilliger says that he learned it from Neumeier, and Neumeier denies any responsibility here. He says that Neumeier says that he never used tensors, but he used scalars. So what I'm going to call zeroth order scaffolds show up in these really nice new papers of Neumeier and Sepet-Penzic, and Neumeier and Penzic have a slightly different definition than I have, and I won't discuss Penzic's work, but what I have, you just missed my joke about you, Paul, but that's good. So the tensors that I have are basically taken from the same François Deschères paper that Akihiro uses as launching point. I'm sure that tensors like this, they're so natural, you'll see that they sort of are a natural linear algebraic object. I'm sure that they probably have been discovered in other parts of mathematics. On Monday, Akihiro Munemasa introduced the partition function for a link diagram. So you have a diagram associated with some drawing of a link, and you have signs on the edges. You saw all of that. And he defined this partition function. So let me vary things a little bit. So I'm going to allow, I call my graph G instead of S. So I'm going to change S to a G. And I want to allow arbitrary edge weights. So here, all of the edges are weighted either with W or the entry-wise inverse of W, which I call W plus and W minus. But now let's just allow for directed edges first off. So I'm going to allow for directed edges. And I want to allow, I'm going to call the graph G. And so that's the first thing. So you have that matrix W. Now I want to allow edge weights to be any matrices whatsoever, not just W and W plus and W minus, but any matrices whatsoever can be the weights on the edges. Okay, and I call it SGW. Okay, so this is a scalar. And this kind of thing you can find in all sorts of combinatorics papers and elsewhere. Now we want to record information. So this is a scalar that's sort of global about the graph, but maybe I want to choose a base point, or I want to look at a couple of vertices and see what's going on relative to those vertices. So I want to allow myself to collect this data in an array or k-dimensional array where I fix any particular elements of X. Then there's a value associated to that choice of values. So what we're going to do is we're going to specify some subset of vertices of our diagram called roots. I use red for root nodes, R1 to Rm, and we have exactly that partition function, but we hold on to the different values for each possible image of the roots. Okay, so this is the definition of a scaffold. So our standard module here, instead of all complex valued functions on X, which Paul calls it function algebra, has the sort of a standard basis X hat. So X hat is the vector, all zeros except there's a 1 in position X. Okay, and now I take each root node and I send it into X, and then I hold on to that hat. So there's these nth order tensors. Okay, so this is the definition of a scaffold. Okay, and the data it concludes the directed graph, the ordered list of root nodes, and the edge weights. Okay, now the directed graph and the root nodes, which I'll make red, And the edge weights are easily drawn pictorially. So instead of having the left-hand side be SGRW, I'll just draw that data, right, pictorially. Okay. So for example, you could see, yes.
What is the X hat? It's like the elementary basis vector of
Yeah.
X?
Yeah, standard basis vector.
So how big is this S of thing? What is its dimension, please?
It's an n-fold tensor. It's an nth order tensor. Complex values on it again, yeah. If you want to think of that. Okay. So for example, if I just take my diagram with no root nodes at all, and I just put the adjacency matrix of a graph on each edge, then I'm just counting homomorphisms. Right? And so you can see Lobos' book on graph limits. The counting homomorphisms has been around for a long time. I think Crystal mentioned that Lobos has used this for a long time. Now, Lobos scales things to see the probability that a random function from my diagram into the target graph, what's the probability that it's a homomorphism? But I won't have that scaling. Also, Neumeyer and Pendrich have a scaling which is useful for their nice theorems on distance regular graphs. Now, when you have the freedom to put in different edge weights, I can also get injective homomorphisms. By putting on all the things that are not joined, I can put a j minus I to make sure that they go to distinct vertices. So injective homomorphisms are easily counted by putting edge weights j minus I. I can also make induced. I can count the number of induced subgraphs that are isomorphic to this graph by putting the complement adjacency matrix on all of those other edges. So you can count homomorphisms, you can count injections, and you can count induced subgraphs. With no red nodes at all. These are just scalars. It's been around for a long time, this idea. Okay, but let's toss in some red nodes. Okay, so here's the definition, and I'll keep the definition up for a while. Okay, so now your homework is, your exercise is, what is a red node with a single loop? Node, I'm summing over all elements of X. So now I'm looking at this matrix M. I'm summing over all rows of M, but I'm only taking the XX entry, right? And that's the vector that's the diagonal. What happens if I make that red node hollow? So now it's exactly the same sum, except I don't keep track of the values. Make that hollow, that's the trace, right? What happens if I take the scalar, where I just sum over all entries, all rows, all possible columns? That's just the sum of the entries of the matrix. What happens if I take that diagram and I make the left dot red? Dot red, then for each row, I'm fixing the row and I'm summing over all values in that column sums, right? It's just a vector of row sums. And what happens if I make the right-hand dot red and the left-hand dot hollow? So the column sums, right? And what if they're both red? Well, I want that to be the matrix M. But you know that the matrix M is really an element of the tensor product of the dual vector space with the vector space, right? So in order for all of us to sort of work nicely, I have to establish an isomorphism between the space of linear functionals and the vector space so that I can identify matrices as elements of the second order, the second order tensors. So to identify that vector space with this, I choose the sort of standard Hermitian inner product. And now I'm going to think of matrices as just scaffolds with two red nodes.
Phil, sorry, Ed.
Yes, that's a great kind of.
Half people are like nodding their head getting it, but I must be missing something, and this seems like a super important slide for the rest of what you're going to be saying. So, like, where is the M, the capital M, coming into this? Is that somehow?
That's the edge weight. So every edge is going to be weighted by a matrix.
By a matrix.
And this is any matrix M with rows and columns indexed by X.
Okay, that's
great question. Great question.
Being that W, and I see a lowercase w.
There's no
a single scalar.
There's no M up there.
Okay.
Thank you, Emily. There's no M up there. Any other questions? That's the next question. I don't know how to make the determinant. That's not the kind of sum I'm studying.
All right, if you go back to 1 second, so I can reference back. I know it's online, but
now what happens if I have a hollow node and I have two matrices, matrix M and a matrix M? This is the sum over, let's say, my nodes here of my diagram are A, B, and C. So I'm mapping A, B, and C to the sets of rows and columns of X. And I'm taking, let me call little x the image of A, and little y the image of B, and little z the image of C. I'm taking the x by entry of M and the y z entry of N, but I'm only recording where X is and where Z is, and I'm just summing over all Y's. So let's throw away the A, B, and C and realize that this is just a sum over all X and Y. It's the sum over all X, Y, and Z, where I can reorder the sums, and that's exactly the product, the two matrices, written as a second order tensor. So series reduction is matrix multiplication, and parallel reduction is entry-wise multiplication. Okay? So now the two multiplications I'm interested in the world of association schemes correspond to things in graph theory that are very fundamental, right? By the way, I'm using directed diagrams. So if I change the direction, that's just taking the transpose. Okay, but most of what I'm going to do here is with symmetric matrix. So that's their algebra. Now you can start doing that series parallel reduction. This diagram right here, this is an entry-wise product of EI and EJ, and then that's the matrix product times EK, and that, you know, from if you know the basic identities of association schemes, that's exactly pulling out the EK component of the expansion of EI entry-wise EJ. What is if I take the dual object is where I take AI matrix product AJ, that's this sum right here, I take the entry-wise product of that with AK, I'm just pulling out that component. Today and tomorrow I'm going to use these things a lot. Also, the all-ones matrix, if you look at the definition of a scaffold, if one edge weight is the all-ones matrix, it doesn't affect the sum at all. So you can stick all-ones matrices in and out. If you find an all-ones matrix on an edge, you can pull it out if it's convenient for you. You can take any two nodes that aren't joined and join them by an all-ones matrix. They're completely disposable. But the all-ones matrix is the sum of the A's, right? So we get linear expansions. Everything here is going to be linear. And then the identity matrix, the only function sigma into X that are going to give me a non-zero contribution with these two nodes is when this sigma of this node, let's call it A and B, sigma of A is equal to sigma of B, which is exactly the same as just collapsing the two things. So identity matrices, you have contraction, all ones matrices, you have deletion. So you have deletion and contraction, you have series of parallel reduction. Fundamental thing that I won't prove for you, but we pretty much have a proof. Right? So EI, entry-wise EJ, entry-wise EK, you sum up all the entries of that entry-wise product, and that's the symmetrized crime parameter. So this sum, we're going to use this later today, when we proved, or actually you're going to prove Dickie's lemma as homework. Okay, but when we prove Suzuki's theorem, we're going to use the fact that as soon as I see that sum is zero, that means that the crime parameter is zero. Okay, that sum is zero if and only if the crime parameter is zero. Fundamental sort of star triangle relations, we proved this yesterday, that Qijk is zero if and only if this third order tensor is zero. Let's think of choosing any three vertices. This is there's a quantifier here over all vertices, all vertices, all vertices at each red dot. Okay, so if I fix a vertex X and I fix a vertex Y, fix a vertex Z in my association scheme, the only way that simple tensor can elementary tensor can contribute something non-zero is if X is I related to Y and Z is K related to Y and Z is J related to X. Otherwise, that's zero. And if there are no such triangles in the association scheme, then every single component is zero. So therefore, the entire tensor is zero. Likewise, if you choose three vertices and you sum over all of these, this is the sum that we had yesterday. It's the basic lemma of Cameron, Hotels, and Seidel, which drops so much of what are in triangle familiar to you from various parts of combinatorics, in particular knot theory. The scaffold of a link diagram. Now I give you a link diagram, and Akihiro showed you how to build the sine graph, and you have these edge weights, W plus and W minus, depending on how the crossings work. So every single diagram of a given link has the zeroth order scaffold. And the whole idea of spin models is to find out what rule on W plus and W minus makes those scalars all equal. Well, it's this type 1 thing that's scaling that's best left aside for a little while. So here's I just reviewed. I mean, I'm not going to talk about spin models. Akihiro is the expert, and he's giving you a lot. But this is a non-symmetric spin model. So we have matrix W plus and W minus. That is, you can think of W plus as a W, and W minus is its entry-wise inverse. Okay. And we want to satisfy these conditions. So in order to get the spin model of the type 1 relation, W plus has to have constant diagonal and constant row sum, constant column sum. W minus has to have constant diagonal, constant row sum, constant column sum. And W plus entry at W minus should be the all ones matrix, and yet W plus matrix multiplied W minus should be a constant times the identity matrix. And then there's this amazing type 3 relation where up here had denominators, right? But remember, W minus is just an inverse of an entry of W plus. So it would make a lot more sense to do it his way. Here are those identities exactly in terms of scaffolds. So W plus, the diagonal of W plus should be all alphas. So that's the entry-wise product of W plus with the identity matrix should be alpha times the identity matrix. The row sum of W plus. So if I just sum up over all the rows, and I should get just this constant, the alpha inverse, the scaffold with no edges. But the interesting thing here, well, first, the entry-wise product of the two is the all ones matrix, which is just no edge at all. And the product of the two is a constant times the identity. And then the star triangle relations, very reminiscent. So here you have in these tensors related to Bose-Mesner algebras, you've got some star equal to some triangle. If every star is a linear combination of triangles, what does that mean? If every triangle is a linear combination of stars, what does that mean? That's all sorts of unsolved problems here, and my understanding is very minimal. So let's just take inner product. So you take the standard inner product on tensors, where the inner product of first component, second component, tensor third component, and first component, tensor second component, tensor third is just the inner product of the first with the first, second with the second, and third with the third. Standard inner product, let me work over the real numbers because I don't want to have to conjugate things. So let me just assume that everything is real. What that corresponds to with diagrams, now I have to have I have to figure out which one is the first red node and which one's the second, which one is the third. So I'm just going to have this convention that they're displayed consistently in space. This happens throughout mathematics, that we have an understanding that arrangement implies inversion. So all you have to do is basically glue these two nodes together and make them hollow. Or sometimes, for me, it's easier to just put an identity matrix between the corresponding nodes, and you get a scalar. And like for the Peterson graph, here's a star and a triangle whose inner product is a negative number, which kind of surprised me. Okay, so this inner product we're going to use later.
When you're writing the inner product, assuming that the vectors have the same labels. You create a diagram and get it.
Oh yeah. There's the first red node and the second red node and the third red node, and we're going to just have a convention that they're going to have to be placed in the same exact spot. If I overlay the diagrams, the dot should overlay. Right? I don't think there's any ambiguity, but it requires some intuition. Right? Here's this lemma from Suzuki's paper. So I call it the isthmus lemma, again, like yesterday. I make up names for things, okay, because it's the way I hold on to things. So the isthmus lemma says, if I have such a diagram, then this right here, know that for everything except H, either JKE is 0 or LME is 0, then the only thing that survives in the expansion, linear expansion of that, is EH. And likewise here, if for all H, if all E except H, QJKE is 0, or QLME is 0, or both, then I can just replace, I can split that node and put an H in there. And now the proof is going to be entirely in terms of diagrams. I haven't proven all the little bits and pieces, but I hope that I can wave my hands a little bit and have you believe that. Okay, so the first thing is that I can take that diagram and I can split a node and put an identity. All the functions sigma into x that give me a non-zero contribution must send those two nodes to the same spot. So that's the same thing as them being one node. Okay. Now, these things are linear. We're working with tensors, so this is linear over any single edge. So therefore, the identity is the sum of projections onto the eigenspaces. And now you have to take it sort of, you have to think, if QJKE is 0, then the tensor right here would be 0. And this is just an inner product, sort of a partial inner product, I guess, of that with this tensor over here. And so the entire thing is 0. So if you have any node of degree 3, right, those star and triangle identities apply inside a sub-object of any diagram, as long as that middle node has no other neighbors, right? As long as there's no other neighbors of that node, then if that prime parameter is 0, then the entire diagram is 0. The only thing that survives is EH. I'm going to use this for the rest of today. I want to slow down.
Sorry.
Yeah.
So you were taking these scaffolds and now it's like some sort of algebra over complex numbers, and this is a real computation.
These are tensors. Yeah, these are first order tensors.
How do you know the dimension of the tensor? Number of red vertices?
Yeah. That's the definition. Yeah. So it's linear over the weights of any single edge, right? You can apply linearity on any single edge.
Are they always going to be trees?
No.
They're not.
No, there's a lot more coming.
So it's
Okay.
still linear even when it's not a tree? I'm sorry.
Yeah, the tensors is linear. Any fixed edge, you can. So here's the theorem that I want to focus on today. And these hypotheses seem kind of complicated. So assume that we have a cometric association scheme, and assume that all of the ledge labels I'm going to use up to H plus I plus J, all of those things make sense. They're inside they're inside the range 0 to D. Okay, so everything I'm going to write down is between 0 and D. And here's the isthmus that we're going to use, J H plus I E. Let me write that down because you're going to see me use it. Q J H plus I, whoops, is 0, or Q I minus J H plus J E is 0, except for E equal to H plus I minus J. So we're going to assume that. Now let's start with this prime parameter equal to 0. Okay, I, H plus J, H plus I. The proof is going to be just a sequence of scaffolds and scaffolds, actually. Scaffolds that are all equal to the 0 scaffold, third order tensor here. Okay, we begin with the assumption that Q, I, H plus J, H plus I is 0. Okay, that tells us that this star diagram is the 0 tensor. Okay, that's the lemma of Cameron, Hotels, and Seidel. Now remember that multiplying EI times the entry-wise product of EJ and EI minus J is a scalar multiple of EI. I have to make sure that that prime parameter is non-zero, because even if it was 0, I could go one way. But if it's non-zero, then I can go this way, and I know that prime parameter is non-zero because of the cometric condition.
Sorry,
Okay.
why is that the imperial product with both of them are white or empty at the?
This one right here?
Yeah, I
So-
thought that was for red and red.
Is this right here? Entry-wise product times a matrix product is just a scalar times this one. Right, and what's happening here is that I'm going backwards, and I need this to be non-zero in order to be able to go backwards. So I'm going from here to here, from the single edge to this little diagram, knowing that prime parameter is non-zero. Now look at this node of degree 4. I can split that node and replace it with an identity matrix between two nodes. Okay, and that identity matrix is the sum of a whole bunch of E sub E. And now we have this assumption that every single E gives me a 0 either here or here, except possibly H plus I plus J. It's the only one that can give me a non-zero, so therefore I can replace the identity matrix with that single primitive idempotent. Now we have this third order scaffold, and that's a third order tensor that's equal to 0. Now, of course, you can write, I'm going to show you Suzuki's proof afterwards, right? You can just fix the 3 red nodes, choose the vertices, and replace all of this by sums. Okay. So now that tensor is 0. So I can take an inner product of that tensor with any other tensor. It must be the 0 scalar. The creativity is figuring out what to take the inner product with. So I have this thing right here, and I want to group on nodes here so that a bunch of stuff is going to simplify. It turns out to be what Suzuki chose. EH plus J on the bottom, EJ and EH plus I plus J. Take the inner product of those two third order tensors, and this is the 0 scalar. From my angle, they all look bold, but I think this edge looks bold to you. So that's the edge I'm going to contract. So now let's apply the isthmus lemma of this edge. How many prime parameters are there going to be non-zero with J, H plus I plus J, and J, H plus I minus J? And H plus I plus J can only go down as far as H plus I, no further down. And J and H plus I minus J can go no further up than H plus I, right? So that's the only thing that gives a non-zero. So I can replace this by the identity matrix, and that's the same exact sum. And now if I replace it by the identity matrix, I can squash that down. Now that quantity is 0. Look over here, J and I minus J Those prime parameters are 0 as soon as I get above I, right? Here, h plus j, h plus I plus j. Well, now I need to I need to use this right here. H plus I plus j, h plus I plus j. The only way you can get there is sorry, this is the one I'm looking at. Sorry, h plus I plus j, h plus j. The only thing that can give me a non-zero here is I. Okay, that's the lowest that one can go. So I can replace that by an identity matrix and collapse it. Now I have an entry-wise product. The parallel edges correspond to entry-wise product. And now I'll expand that in terms of the E basis, the basis of idempotents. Here's the expansion of that edge in terms of the idempotents. And notice that every single one of these is going to give me a 0 scaffold, except that single one, h plus I. It's the only one that's going to give me a potentially non-zero value. So now we have to apply the isthmus lemma again, I think right here. So h plus I minus j, and this is h plus j, I minus j. That's this one right here. So that's the hypothesis we're using right there. So that's 0. So we can apply the isthmus lemma and collapse that one. Now we have this diagram as 0. These are all scalars now. And now this is again that thing that Emily asked about. It's a matrix product times an entry-wise product. And that just becomes a scalar times that particular thing, which is h plus j. Now we have that this little 3 parallel edges is a 0 scalar. And we saw before that can only happen if the prime parameter is 0. So now we get that prime parameter is 0. For me, just seeing it in terms, I guess maybe because I grew up in graph theory, it was a really nice little town. And it just, for me, seeing it in graph theory was a nice way to see it. So, but I want to show you what the original proof looks like. So this is, I'm just taking screenshots of Suzuki's paper. So he has exactly the theorem that we have. And he starts with that little diagram. That's the star diagram that we started with. And then he starts putting this in. All I've done is transcribe his proof. And now this is a triple sum. So therefore there's that's not the triple sum. Sorry, it breaks it. Sorry, this is half of a line. Triple sum, and then and then we have here we have a triple sum followed by another sum. And somewhere in here, there's a 9-fold sum, right? Because there's 9 edges in that big prism. There's 9 edges. So he has a 9-fold sum in here somewhere. And I just don't see it right now. But anyway, this is exactly the proof that I just gave you, just written in sort of classical, get that 9-fold sum. And then he starts collapsing it down. And he gets exactly to the thing that we ended with. So that's your choice. You can write that style or the other style. But I got a feeling that Suzuki was using these diagrams to come up with the proof. And so I'd like us to get to a point where we feel that that's a rigorous way to do association scheme mathematics. And your homework is to prove Dickie's lemma. This was a big result when it came out, but we understand things to the point now that I think that, not to trivialize it at all, but to just show the power of the technique that was developed by these people. If you have an AJ star that's 0, except the last one, then you can just put that into the same diagram, put that into the same machine, turn the crank, and out comes A1 star equal to 0. Here's another thing that Suzuki did was collapse. You can collapse the complete graph K4 in 2 different ways and get interesting information. So you can say, if for all E not equal to L, so this is an isthmus assumption, for all E not equal to L, HME is 0 or IKE is 0. And for all E not equal to M, HLE is 0 or JKE is 0. One or the other or both. Okay. Then these 2 prime parameters, KLI and KMJ, must be equal. You take this K4 diagram, you choose the edges properly. Now, this is just a scalar. There's no tensor here. This is just a scalar, but it's a 6-fold sum, right? It's a 6-fold sum. And now you see that IKE is 0 or MHE is 0 except for E equal to L. So I can squash those 2 nodes together. One of the hypotheses was IKE or HME, one of those is 0 except for E equal to L. IKE, HME, all of the E's disappear except for that particular one. Now you have this little pinch star, right? So you have EJ times EK, EM, and now you know that the only thing that shows up is the scalar KMJ times this. But now rearrange the Q4, right? And put M over here, and one of the hypotheses is HLE or JKE, whoops, E, oh no, here it is, HLE or JKE, one of those is 0, except for E equal to M. So that means that you can collapse that edge. Okay, once you collapse that edge, now you apply that pinch star, this entry-wise product times a matrix product, and now you get this scalar multiple of this diagram is exactly this scalar multiple of this diagram. But this, we assume is non-zero, so therefore the only way that can happen is for those two diagrams to be 0. I'm sorry, I said something incorrect. I apologize. This quantity right here is assumed to be non-zero, and so the only way these two things can be equal is if those two prime parameters are 0. I said diagrams. The boxed-in lemma that I used yesterday is just a special case of this. Okay, so if I have in some Krein array, if in some Krein array L sub R star, somewhere I have Q RST not equal to 0, and in row 1 lower, I have zeros, and in column 1 higher, I have zeros. So I have zeros here, 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 and here. Then we get equality of 2 entries in the Krein array, right? We get that CT star is equal to BS star. It's exactly that theorem where you just turn the crank and plug in those values. Okay, so you can do the same thing for the other parts of the boxed-in lemma. Okay. By the way, I have printed copies of the notes. If anybody's actually reading the notes and you'd like to see more errors, I can get you a printed. Triple intersection numbers have become an interesting thing in distance regular graphs. So Chris Coulthard and Sasha Juricic define these generalized intersection numbers. So fixed vertices A1 up to AK in an association scheme and fixed distances I1 up to IK. Say how many vertices are distance I1 from A1 or in relation I1 to A1, distance I2 from A2, etc. Depends usually on the choice of those base points, right? But we can just choose every possible base point with the scaffold and just write this down as this tensor. So you know that you can always write those down as a tensor, okay? Now, when K is very small, 1 or 2, sometimes 3, if you have triple regularity, this doesn't depend on the choice of the base points, right? And this is a very nice tensor. Coulthard and Juricic used the fact that even though it's not independent of the base points, this gives you an identity because each of the E's, each of those edge weights is a linear combination of A's, right? So if that Krein parameter is 0, then you can expand that edge, which was E sub R, that was E sub S, expand that in terms of the A's. You can take the E sub R and expand that in terms of the A's, and you can take the E sub T and expand that in terms of the A's, and by linearity, this linear combination of much more combinatorially accessible tensors must be. Terwilliger proved, I think he can do this long before that. So the tensors where the Krein parameter is positive, they form an orthogonal basis for the space of all possible tensors in the Bose-Mesner algebra. That space of all possible tensors has this as a basis. I think this is sort of in his 1989 paper. We're going to talk about these vector spaces of tensors tomorrow, because these spaces are really, really nice. Okay, so the triple intersection numbers are there, but do I have time to go a little bit further? I have time to go a little bit further. Well, I skip the cartoon?
Yeah.
Because it said end. Yeah, I thought I would run out of time. So I'm going to go a little bit further. I'll come back to the cartoon, I promise. So now we have a vector space A, and we really want it to be a coherent algebra. We have a vector space A, and we have some diagram with M root nodes. Now we'll take the vector space, so bold W, this is taken from Paul's 1989 paper, he used the W, bold W that diagram with edge weights in A is the vector space spanned by all possible scaffolds you can build, where you have that diagram and edge weights from that algebra A. So assume A is a coherent algebra or cellular algebra. If the graph is K2 and all the vertices are red, then this diagram, this vector space, which now I'm going to just replace the rooted diagram by this picture right here, is exactly the Bose-Mesner algebra, or exactly the coherent algebra. The edges, that's the coherent algebra. But in fact, you probably see already, anything that's series parallel reducible to a single edge, you're still exactly in the coherent algebra because it's closed under entry-wise and matrix multiplication. So you can check that if the number of edges is at most 4, then there's no way to get outside the Bose-Mesner algebra. But if you take this K4 minus an edge, this differentiates the Shrakhandi graph from the complete graph. You apply this to a Doob graph, and you get something outside the Bose-Mesner algebra. Apply that to a Doob graph, you get a different thing than you have inside the Bose-Mesner algebra. So very quickly, the vector space becomes bigger than the Bose-Mesner algebra. Okay? Well, actually, I haven't proven to you that it contains the Bose-Mesner algebra, have I? It's a coherent algebra. So the matrix algebra, so the algebra of all matrices, complex entries, rows and columns indexed by X, I'm going to call that mat XC. And a coherent algebra is a vector subspace, which is closed under conjugate transpose, closed under matrix multiplication, closed under entry-wise multiplication, and contains the identity for each of those multiplications. You see very quickly that this is the natural thing to assume for the vector space of edge weights. Okay? So if that coherent algebra or cellular algebra is commutative, then it's called a Bose-Mesner algebra. So these were introduced. The coherent algebras were introduced by Donald Higman in 1987, and here he is with Tatsuro Ito and Francois Gégé. I know a lot of you have this photo, but it's a precious photo for our research community. The three of them in Kyoto, and I don't know the year. Does anyone know? You were there, I bet. You know the year? 91, 93. Now, if you take the space of all possible tensors with edge weight, with the diagram of the triangle and edge weights in the Bose-Mesner algebra, Terwilliger proved that this set of triangles with edge weights AI, AJ, AK, this is this EJ star, AK, EI star, right? If you're a Terwilliger algebra person, that this set forms an orthogonal basis for that subspace of tensors. And if you dualize the set EI, EJ, EK with prime parameters positive, is an orthogonal basis for this vector space of tensors. And this is EK, EJ star, EI, if you're a Terwilliger algebra person. The idea of graph minors comes up very quickly, right? So graph minor, the basic idea is you take edges that are not joining two root nodes, and you can contract them or delete them. Okay, contract or delete any edges that are not root nodes, and you can throw away isolated vertices, I guess. Have a rooted minor, so that's a rooted minor, you have to hold on to the root nodes. If you have edge weights in a coherent algebra, and the diagram H with root nodes R, and diagram G with root nodes R prime, and you have to identify. I left out some detail about the relationship between R and R prime when I dragged this from the paper. That this vector space is the subspace of this one. So now you can go back to that example right here and see that this does contain the Bose-Mesner algebra because I can contract that edge, right? I can take all the diagram, I can take all the scaffolds where that weight is the identity, right? And that means I'm contracting that edge. And now I have a series parallel reduction, so therefore I can, for example, you could just put anything in the Bose-Mesner algebra here and put an identity matrix on these others and a J here, like put a J here, identity, 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 and put any matrix you want there. So you can very quickly see that you can choose edge weights to get any scaffold that has a diagram that's a minor of the one that you have. Okay, so now there's this containment to these vector spaces. You start with Bose-Mesner algebra, that's the simplest thing if you have two red dots, and then it grows. Okay, so for example, for third order tensors, a lot of this is in Paul's paper from the 1980s. Third order scaffolds. You have this this diagram here This space of scaffolds is contained in both this and this because it's a subgraph of this one and it's a minor of this one. I can contract an edge here, I can delete an edge to get down to that one. Here at K4, if I delete those edges in the middle, right, I get this. So that's a subspace of that one, and this is the subspace of this one by contracting those edges. Okay, so this tower goes up, right? But you see that this one showed up in the Suzuki and Dickie proofs. Right? This space was useful. So we've already gone up to this space in our very introduction to the topic. And so working with these tensors, it's useful to know which one is a subspace of which one. Sometimes the poset collapses. Oh, am I out of time? No, I still have a little bit of time, right? So the Peterson graph, P111 is 0. So this space has dimension 14, right? Because that's the number Paul proved that is the number of non-zero PIJKs. So the dimension of that is 14, but the space of all third order scaffolds that you can build with edge weights in the Bose-Mesner algebra, the Peterson graph, has dimension 15. So there's something in there that's not expressible in this way. Now here's the triply regular condition. If the triangle space, if the vector space of scaffolds on K3 is contained in this space of scaffolds, or this one is contained in the other one, then you have that this thing is just the Bose-Mesner algebra. So for the Doob graphs, you don't have this. So therefore, one of these two must fail for Doob graphs. We'll talk about tomorrow is these vector spaces of scaffolds. And one way to view the Terwilliger algebra is choose all possible base points. So this is in Terwilliger's paper 1987. You can take a third order tensor and just think of it as a big block diagonal matrix. So you've got matrix, you choose one base point, there's a matrix, you choose another base point, there's another matrix on the diagonal, choose another base point, there's another matrix. Just build a block diagonal matrix of Terwilliger algebras, and that is as a vector space at least isomorphic to this space of third order tensors. And so now these are the star elements of M star, and these are the elements of M. Paul can explain this much better than I can. So if you take the union or the sum of all these spaces, I guess I should say sum. I don't know why I wrote union. Maybe it is a union. I call that script T. I think I won't try to guess what Paul did, but he decided that matrices are easier to handle. We have a theory that handles matrices. So although he introduced the third order tensors, he quickly went, when you have that paper on the balanced set condition, he quickly went to the matrices by fixing a base point, right? And then you can delete that node. So the most basic third order forms of these star and triangle relations. So for example, it's right here, you have that triangle, you have this and this where you have the L1's matrix. So that still has, I'm just embedding that in those graphs. Oops, in this slide, right? I want to show that star and triangle is a special case of this, right? So the triangle, I didn't have to do any work. For the star, I have to add in L1's matrices. Okay. Now the product, if you want to capture the Terwilliger algebra product on third order scaffolds, then you have to make up some silly rule that sort of these are the matrices that we see when we talk about Terwilliger algebras. You can multiply the matrices, but now you have to identify the base points, right? You have to identify base points and keep that red. So with that product and linearity, that's isomorphic to the direct sum of Terwilliger algebras with all base points. And long ago, he decided to work with matrix theory, and we haven't seen this unless we dig into his paper. Triple regularity. So suppose we have a symmetric association scheme. Let's say it's triply regular. If when I choose three vertices and I know the relations between them, then for any other relations, let me call these relations I, J, and K. For any relations R, S, and T, I want to know exactly how many things are distance R from the first, S from the second, or it's not just an association scheme. R related to the first vertex, S related to the second vertex, and T related to the third. That should only depend on the outside triangle, the relation between the three. Okay, so that means that these two vector spaces are equal. And then you can dualize this, right? So all of this there's planar duality going on here, but it's actually circular planar duality. You're embedding your graph in a disk, and you're taking the circular planar dual. I don't know if you've seen the definition of a circular planar dual of a graph. Okay, it's a dually triply regular. You take the dual of these things, and you can write down this definition. And I haven't studied it. There are tons of open problems here. Right? as Paul points out, he said, not even clear what happens for the complete graph if the association scheme of the Bose-Mesner algebra is the complete graph. These algebras each have some interesting structure. So if you have a coherent algebra, we had this poset, but now we're assuming, right, if it's strictly regular, then this is equal to this, so the poset collapses. If it's duly strictly regular, then this is equal to this, so the poset collapses. And so, I think I'll talk about that collapse tomorrow. But this is probably a reasonable time to stop. And for Emily, go back to there. Thank you for your time. Yes.
Can you use scaffolds to prove that if you're triply regular, then you're dually triply regular?
We use
Scaffolds to prove that if you're triply regular, then you're also dually triply regular. There's some delta line transform, maybe.
I'm not sure if they're the same concept. Do you think they're the same or do you think they're different?
In Pole's classification, they were all formally self-dual. So
Right, if it's formally self-dual, yeah. But I don't know if association, I don't know if coherent algebras that have both properties, that have either property, I don't know if the two properties are equivalent. So I went the wrong way. So
but do you know any triply regular thing that is not dually triply regular?
I would conjecture that they're different concepts, but I cannot prove that.
In your classification, there is none.
This has always been a little obscure to me. It's not clear to me if the the W on the top is the same as the W on the bottom on the left.
Yeah, we know schemes where those two are different, but I'm not sure. Yeah, I know what you're saying. We know we know that these two are different, but if you assume that these two are equal. Are these two equal? That's an interesting question. Let's work on it over lunch.
No, I have to make my talk.
Okay, you have to put the talk. But there are lots of open questions. This is just, I published the paper last year in linear algebra and applications. And then tomorrow I'll talk about this really nice result of Liang, Tan, Tanaka, and Wang that proved a corrected version of my conjecture for translation schemes.
The scaffold has this way of dealing with multiplication using graph operations, the edge deletion or edge contraction. Can you come up with a graph operation on the scaffold that deals with expanding sums or turning A plus B?
Just some of scaffolds. I would just do linearity. All of this, that's why this W is natural, because you're taking sums where you're just linear over the edges. Right, so I would just write that as a sum of a linear combination of diagrams.
So if I had A plus B on one of my scaffolds, you just split that into two scaffolds.
Yeah, one with an A and one with a B. Yeah, I've been doing that today. I don't think there's a graph theoretic way to handle that. I think the basic linear algebra is much more direct.
It's an algebra where those things are the elements. It's an algebra over.
Right. He's just saying that it'd be really nice if there was a graph theoretic explanation for other basic things. Anything else? Jay?
My question might be a bit vague, but I was wondering if we obtain the new characterization of a Q-polynomial association scheme using scaffolds.
I don't see any. I guess you could, you can write down the P-polynomial and Q-polynomial conditions as a bunch of scaffold equations and non-equations, because remember, you need some Qijks to be non-zero to be Q-polynomial. So you can write down the P-polynomial condition and Q-polynomial condition for fixed D as a finite list of scaffold equations, but I don't think it gives us much of an advantage. I don't see anything really quick and elegant.
So you talked about the identity having a natural interpretation in terms of scaffolds, also the all ones matrix. What about the center of the T algebra? A central element. Yes, in that picture.
If in the matrix form, it's a central element.
Right. So maybe there's some natural scaffold theoretic sort of way to recognize it. That's some linear combination of diagrams is central in the T algebra, or more generally.
That's a nice idea.
Yeah, that would be very wondered for a long time now how to describe the center of the T algebra. There's really not much about it at all in the literature at the moment.
in an early version of my notes, I had this, this silly, oh my gosh, the chalk is so soft that Mn is equal to Nm if they commute, right? It just seems like it's so incredibly useful in the linear algebra setting that being able to move these edges and then let the other matrix play off against the other edges coming into that vertex. But it didn't seem like something that I could really incorporate into the diagram manipulation.
Yeah, so the central thing in T would have to be some combination of diagrams of that general sort. That would have the property that if you sort of attach an extra triangle on one end, you can sort of pull it through.
Right. If T is a single, just a single triangle or star, you can pull it to the other side. Really nice. There's so many things I want to study, and I hope that you folks. I told you this set of talks is a plea for help. It's a cry for help. There's so many things in the Q-polynomial world that are unsolved.
So we have those fundamental relations. I call them the triple product relations. In your picture, look like forbidden triangle, so to speak, and then forbidden star, so to speak.
Right.
Could there be? It would be great to find higher order forbidden configurations that aren't forbidden simply because they follow from the forbiddenness of the third order scaffolds. I mean, maybe just a wild guess. Maybe these forbidden things are the first in a series of forbidden things. The higher order things not logically following from the forbiddenness.
Yeah, not just having a vertex of degree 3 like this, but something more complicated, and yet you can. Yeah, this is something I've actually tried to do. I have minimal results in that direction, but this is really nice.
Yeah, this would be if it turned out to exist. These higher order forbidden things.
Yeah, I think everything that I have so far, like with 4 dots, four root nodes, it's kind of obvious that it follows from this, right?